Hello everyone, welcome to today's video. Today's video is about characteristic polynomials, which are the way we have to compute the eigenvalues of a matrix. We saw last time, after defining eigenvector and eigenvalues, a way to find eigenvectors once we know the eigenvalues. Today we focus on finding the eigenvalues. Let me remind you from last time that the eigenvector of a matrix is a non-zero solution of a homogeneous linear system with associated matrix A minus lambda I, where lambda is an eigenvalue of the matrix A. The idea we will follow to find eigenvalues is to try to determine for which values of lambda such non-zero solutions of homogeneous linear system even exist. So the question that we want to answer is, when does A minus lambda I even has a non-zero solution? We have seen in the past that requiring that a homogeneous linear system has non-zero solution is the same as requiring that the columns of the matrix of the system, A minus lambda I, are linearly dependent. This is another way of saying that we want A minus lambda I to be not invertible, or in a way that is actually way more computable for us. Equivalently, we want to say that the determinant of A minus lambda I is equal to 0. That is an equivalent definition to the fact that the homogeneous linear system has non-zero solutions. In other words, the idea behind this is that the eigenvalues are zeros of the quantity determinant of A minus lambda I seen as a function of lambda. Let's have a look at some examples. Here's a 2x2 matrix, and we want to find its eigenvalues. So the first thing we do is to look at the matrix A minus lambda I. We treat lambda as a variable here. So we subtract lambda times the identity, which is the matrix 0, lambda 0, 0, lambda. The resulting matrix is 3 minus lambda minus 3, 2, 8 minus lambda. Now, let's compute the determinant of the matrix A minus lambda I. This is given by 3 minus lambda times 8 minus lambda plus 3/2, the entries on the off diagonal. We can expand this product a little bit, and we get that this is lambda squared minus 8 lambda minus 3 lambda plus 24 plus 6. In other words, we get that this is lambda squared minus 11 lambda plus 30. Now, we want to ask ourselves the question, when does for which values of lambda is this equal to 0? In other words, we can solve this, we want to solve this quadratic equation. In this particular case, you can observe that this polynomial actually factors. It factors into lambda minus 5 times lambda minus 6, I believe, because minus 5 minus 6 is minus 11, and minus 5 times minus 6 is 30. So the eigenvalues of our matrix A are precisely the zeros of its determinant. So yeah, we want to solve this for 0. And that's 0 whenever lambda is equal to 6 or lambda is equal to 5. Those are our two eigenvalues. Let's have a look at another example. The approach is very similar. To find eigenvalues, you always want to start by looking at the matrix A minus lambda I. This time I will skip the step and I will just write the matrix by subtracting lambdas. -4, -4, -2, minus lambda. And then we want to take the determinant of it. This determinant is going to be given by 2 minus lambda. I can do a cofactor expansion across the first column, for example. It will be 2 minus lambda times the determinant of the rest, which is 2 plus lambda squared. That's -2 minus lambda times -2 minus lambda, minus 16. Let's try to clean this up a little bit. We have, my goal is to find the zeros of this polynomial. So it's in my interest to leave factors as they are. But I want to factor the rest, so I will have to deal with that. This is lambda squared plus 4 lambda plus 4 minus 16. So now we have a +4 and a -12. So I suppose we can factor that polynomial into 2 factors. If I want to get +4 and -12, I should probably get lambda plus 6 and lambda -2. So we can write this as follows. Allow me to change one sign so that I have lambda -2 instead of 2 minus lambda. So I have lambda -2 squared times lambda plus 6. So the eigenvalues are lambda 1 equal 2 and lambda 2 equal 6, the roots of this polynomial. We saw in these examples that the determinant of A minus lambda I is actually a polynomial with the variable lambda. And it's a very important polynomial to the point that we give it a name, and we call it the characteristic polynomial of the matrix A. By definition, the characteristic polynomial P of lambda is the determinant of the matrix A minus lambda times the identity. And by what we just saw and the argument we did above, the eigenvalues of lambda correspond exactly to the roots of its characteristic polynomial. In the example above, the characteristic polynomial that we computed was, there's a minus. It was minus lambda -2 squared times lambda plus 6. And sorry for that. The root of this polynomial is actually -6. And the eigenvalues are 2 and -6. I want to point out at this moment that it will play a significant role later, the fact that 2 appears twice as a root because there's an exponent 2. We'll come back to that in a second, but before moving on to that, I just want to mention one other thing that could happen, which is the fact that some matrices do not have real eigenvalues. There are matrices whose eigenvalues are complex. And we will not talk about those very much in this class, but it's important to keep in mind that it's not automatic that any matrix has real eigenvalues. Some of them don't. You can even find very simple examples of matrices that don't have real eigenvalues. This matrix here is actually a matrix rotation associated with a rotation of 90 degrees. But it's also very simple, 0, -1, 1, 0. However, when you start taking its characteristic polynomial, you see that this matrix minus lambda I becomes minus lambda -1, 1 minus lambda. And when I take the determinant of that, that determinant becomes lambda squared plus 1. Now this polynomial here has no real zeros. In fact, if you have seen some complex numbers, you can probably understand from here that the roots of lambda squared plus 1 are lambda 1 equal I, the imaginary unit, and lambda 2 equals minus I, where the imaginary unit is defined by its squared being equal to minus 1. We won't delve further in this, but it's something that it's good to be aware of. Okay, in the next video, we'll talk more about the role played by these exponents, also called the multiplicities of eigenvalues.